7.3 Applications of the dot product. So not a lot of new notes here. Mostly we're just going to talk about some of the specific applications. One thing we're going to talk about is just determining the work done. That's something we already did a little bit last lesson. We're going to also be able to use it if we're not given the angle between two vectors. We're going to be able to find the angle between two vectors. And then one new thing that we're going to look at is called vector projections. So basically, you can think of this as a shadow. We'll get into notes, but it's basically what does this vector v look like when it's projected onto vector u, and it's basically like a shadow coming down and causing this to be the projection of vector v onto vector u. So that'll make sense as we do it. So right away into example 1. Example 1 is find the work done. And we have Angela. Angela has entered the wheelchair division of a marathon race. While training, she races her wheelchair up a 300-meter hill. So I'm just going to take notes on what I'm coming across in the problem. 300-meter hill with a constant force of 500 newtons applied at an angle of 30 degrees to the surface of the hill, to the surface of the hill. We need to find the work done by Angela to the nearest 100 joules. All right, well, I could draw this out for us, but we might even be at the point where we can do this without drawing a diagram. She's going up a hill. Okay, she's applying, so this is our displacement vector then, right? Displacement, S. She's applying force at an angle of 30 degrees to the hill itself. So theta is 30. How much force is 500 newtons? Okay, that is the magnitude of force vector. I'm just going to call this force with a little arrow on top. So there's our diagram. So F is the force vector, S is the displacement vector, work done, capital W, then is the dot product of F and S. The dot product is the magnitude of S times the magnitude of the force in the direction of, so the component vector of the force vector in the direction of S. So that's the magnitude of S times the magnitude of F times the cosine of 30 degrees. We are told that the hill is 300 meters. 300. We're told that her force is 500 newtons. 500. Cosine of 30. I guess I should have generalized this as theta at first. And then we carefully put that in our calculator. We end up with approximately 129,904. And this is measured in Newton meters. Find the work done by Angela to the nearest 100 joules. So the work done is approximately 129,900 Newton meters, or 129,900 joules. Two ways of measuring the energy expended or the work being done. Example 2. Example 2, this is the angle between two vectors. So we're determining the angle between two vectors. There are two different problems. There's an A and a B. So A, we're given the vector G as 5, 1, Cartesian vector. and h as -3, 8. And from the definition of the dot product, we know, so this is the solution. So from the definition of the dot product, we know g dot h is equal to the magnitude of g times the magnitude of h times the cosine of theta. Okay? So now what we need to do then is to find the magnitude of g and h. Again, there's two ways you could do this. You could sub in what you know and find first, and then divide both sides by magnitude of gh, or I can do that right now. So right now I can express this as the cosine of theta is equal to divide both sides by the magnitude of g times the magnitude of h. Okay, so it's going to look like in the numerator dot product of g and h, in the denominator the product of the magnitudes of g and of h. The dot product of g and h, we're getting pretty good at it. It's simply taking the first digit for g times the first digit for h, so that's 5 times -3, and we're going to add 1 times 8, g2 times h2. That's the numerator. The denominator now is the magnitude of both of these things. So again, magnitude, we're thinking of a Cartesian. We're at 5, 1, which is like over here. That means this is 5, this is 1. Pythagorean theorem, a squared plus b squared equals c squared. Okay, we're going to do that for g, for the magnitude of g, and then the exact same process for the magnitude of h. So in this denominator, we're looking like square root of 5 squared plus 1 squared times the square root of -3 squared plus 8 squared. Now the only thing I could see you, if you're trying to memorize this, the only thing I could see you mixing up on is that in the numerator you have g1 times h1, and then here you have g2 times h2. Whereas in the denominator, when you're working with just vector g and then just vector h, so your numbers come from g1 squared plus g2 squared, and then the square root of that. And over here you have h1 squared plus h2 squared. Okay, so just that's one area that you might get a little bit mixed up on. All right, I can simplify this before we go any further. So this is -15 plus 8. That's going to be -7 in my numerator. Here I have the square root of 26, square root of 26. Here I have 9 plus 64, 9 plus 64, which is 73, square root of 73. And now I can go ahead and I'm just going to leave it like that so that I'm dealing with an exact value. But now I know that the measure of angle theta is the inverse cosine of -7 over radical 26 times radical 73. You put that carefully in your calculator, or you could even still do it in two parts. You could do this part first and then hit second function inverse cosine of second function answer, and you'll get the measurement of theta as approximately 99.246 degrees, or to round to the nearest tenth would be sufficient. Approximately 99.2 degrees is the angle in between these two vectors g and h. Example 2b, our vectors are s, which is defined by -3, 6, and the vector t, defined by 4, 2. And we're going for the angle in between them. So again, we head for our dot product definition. This time I can skip ahead to what I established in A, that the cosine of theta is going to be the quotient of the dot product ST over the product of the magnitude of S and T. And again, sub in what I know. The dot product of S and T is going to be negative 3 times 4 plus 6 times 2. And the denominator is going to be the magnitude of S times the magnitude of T. Well, the magnitude of S is square root of negative 3 squared plus 6 squared. And the magnitude of T is going to be 4 squared plus 2 squared. Again, simplify this as much as I can before putting anything in the calculator. Negative 12 plus 8 is going to be negative 4 in the numerator. Here we're going to have 9 plus 36, that's 45. So the square root of 45 times the square root of, and here we have 16 plus 4, that's 20. And so now I've got theta is equal to the inverse cosine, and I'm just going to go ANS for answer. I'm going to put that in my calculator. It's going to come out with something. My calculator is going to remember it. I'm going to hit second function, inverse cosine, second function answer, enter. And that's going to give us an angle in between them. Ooh, I did this one wrong. This is not... Again, do as much as I can here before putting it in the calculator. We've got negative 12 here and positive 12 there, so we have 0 in the numerator. I'm going to reduce the denominator just because, but I can see that this is going to change things anytime we get a 0 as cosine of theta equals 0. But I make sure the denominator is not 0, so I should do this. 9 plus 36 is radical 45. And 16 plus 4, that's 20. All right, well, this tells me that the cosine of theta equals 0. Well, if we end up with the cosine of theta equaling 0, then that tells us that theta must be 90 degrees. So these guys are perpendicular to each other. Definition for things, for vectors that are perpendicular to each other, is that they are orthogonal. I'm going to go ahead and give you a little note there. Maybe we'll do it in black over here. S is perpendicular to T because S T, the dot product, equals 0. We wrote a note last lesson that if and only if the dot product equals 0, then we know that these are perpendicular to each other, which also means that if they are found to be perpendicular to each other, then the dot product is 0. So what are we saying? Well, two vectors on any plane, we'll learn that word later, but right now we're just two-dimensional plane, that end up being 90 degrees to one another are called orthogonal. They are orthogonal vectors. So S and T are orthogonal. What does that mean? Vectors that are perpendicular to one another. All right, that wasn't so difficult, and we've also established a little bit of another formula right here. That we can use this formula now to determine the angle theta between two Cartesian vectors, any two Cartesian vectors. Okay, so we're going to be using that one as well. All right, we're going to talk about vector projections. We're going to be talking about the projection of V onto u. Okay, so we have two vectors. They can be any vectors, and we can talk about the projection of vector v onto vector u. Okay, I'm going to draw 3 diagrams. First thing I'm going to do for each diagram is just draw the vector u. And there's kind of 3 options that we would want to talk about. I can take vector v, and if vector v is anywhere in between 0 and 90 degrees, the relationship, the angle between u and v, if it's anywhere between 0 and 90 degrees, okay, let's say v looks like this, then the projection of v onto u is the component vector of v in the direction of vector u. Okay, so it would be from tail to tail to there. That would be the representation of the component vector of v in the direction of vector u. This is also the projection of v onto u. Now, in the case where the angle between them is between 0 and 90, then the projection vector is going the same direction as vector u. Okay? Now, another possibility is that this angle is greater than 90 degrees. Maybe it's in between 0 and 180, so that vector v is doing this. And now, maybe I should better describe the projection. It's kind of like thinking of a light shining down on vector v, and what kind of shadow would it cast on the direction vector u, okay? Same thing here. A light is shining down all across vector v, and what kind of shadow is it casting? Well, this time, the projection of v onto u is actually going the opposite direction of vector u. Okay, so that is another possibility. The projection of v onto u is in the opposite direction of vector u. And then the last one I want to draw is the relationship between u and v is that they're going to hit at a 90-degree angle. So same thing, if the light source is coming down from above, what shadow is v going to cast on u? Well, it's not. There's not going to be anything there. So the projection of v onto u is equal to 0 because there is no shadow. Okay, I'm going to give you just the symbol that we use here. Okay, so this vector, this purple one that I have here, is the projection of vector v onto vector u. It is the component vector of v in the direction of vector u, and we call it, so this language, the projection of vector v onto vector u, can also be said this way, P-R-O-J, the projection of, and then leave a little space here, v with a base of u. This says the projection of vector v onto u. Okay, in this case, it is in in the direction of vector u. It's going the same direction anyway. Same thing here. This right here, this purple guy is the projection of v onto u, and here and in this case, by the way, it would be negative. Is negative. Here is positive. And here, the projection of v onto u equals 0. Okay, this is the terminology for the vector. So this projection of v onto u is a vector. It's this purple vector here in each case. And here you can see they're perpendicular, so the projection is going to be 0. All right, we can apply that in example 3. Example 3, find the projection of one vector onto another. And what this example really does is it's going to help us to generalize the projection of one vector onto another when those vectors meet at an angle of less than 90 degrees, and then what happens if they meet at an angle greater than 90 degrees. So A is the projection of V on U if theta is between 0 and 90 degrees. Okay, so step one, we're going to construct a line segment. We're going to take a diagram. So the diagram that they give us is right here. Looks kind of like this. C, A, B, and theta is here. And you can see that I have two vectors. I have the vector AC, I have the vector AB. They're arranged tail to tail. There's an angle in between them. And we're going to construct the line segment that's going to show us the projection of vector V, V onto vector U. Okay, now that projection forms a 90-degree angle, right angle triangle, and we're going to call that point D. Okay, so now DC is the, I guess I'm going to say vertical component. It's not vertical, but it's the going this direction component of AC. And the line segment AD then is the component vector of V in the direction of AB, of vector U, which means it is the projection of V onto U. Okay, that's familiar so far. So here's our diagram. I've got a right angle triangle. Keep it all nice and neat and organized here. So what did we just say? AD is, or equals, the projection, PROJ, of V onto U. So from the triangle, what do we see? Well, we see the magnitude of vector AD over the magnitude of vector V is equal to the cosine of theta. Well, how did we know that, Mr. V? It's just SOHCAHTOA. Okay, this is, we're in a right angle triangle, so I know that the cosine of angle theta is adjacent over hypotenuse. So adjacent is my projected vector V onto U, and the hypotenuse is the magnitude of vector V. Okay, so it's just AD adjacent over the magnitude of V, which is the hypotenuse. Okay, from here, I'm going to multiply both sides by, in order to isolate the projection vector, in order to isolate the magnitude of AD, I'm going to multiply both sides by the magnitude of V. So we're going to be left with AD equals magnitude of V times the cosine of theta. And we've already stated that AD is the projection of V onto U. So, and I'm going to replace that. And we're talking about magnitude still. So we've got the projection of V onto U. The magnitude of that is equal to the magnitude of vector V times the cosine of theta. All right. All this does is give the magnitude of the projection. Okay, that's what we did. We used a little bit of trigonometry to go from this understanding to saying, okay, well, how do I get the magnitude of this? How do I get the length of this piece? And it's just right here. Okay, so now we have the magnitude of V onto U is represented by the magnitude of V times the cosine of theta, whatever that theta is. And this is going to work in any situation. So this works when the direction of this pink projection is the same direction as the vector U. Okay? So this is the magnitude. This is the magnitude of the projection. I'm going to try to get this all in one line. This is the magnitude of the projection. It is also called the scalar component of V on U. Okay, so this is a scalar component. It's a magnitude. It does not indicate direction of the projection. We know that it is in the direction of U. Okay, well, how do we come up with a situation where we can get the magnitude and the direction of this vector? And the way to do that is to multiply the magnitude of this vector by a unit vector that's going in the direction of the original vector u. So if we had a unit vector going this direction, same direction as u, and we multiplied it by this magnitude, then we would have a full description of this vector. So let's just say to indicate the direction of the projection of V onto U, multiply by a unit vector in the direction of U. Okay, that makes sense. If we took a unit vector going this direction and we multiplied it by the magnitude of the projection that we've just gotten, then we would get a more full description of the vector AD, the projection of V onto U. So what does that look like? So a unit vector and a multiple of it, we're going to let KU be the unit vector in the direction of U. This, hopefully you're remembering this from previous lessons. Essentially you're saying take the vector u, no matter what length it is, there does exist some scalar multiple that will either increase it or reduce it to be 1 unit in length. Okay, so it's heading the direction of u, but there's some scalar multiple that you can do to give it a magnitude of 1. So we're going to let ku be the unit vector that's going in the same direction as u. So it's going in the same direction as u, but it's 1 unit long, just as we've indicated up here. Okay? What next? Well, we already know then, since this is our definition of ku, it's a unit vector, that the magnitude is 1. Well, now let's use some of our properties. That means that the magnitude of k, the scalar value of k, times the magnitude of u equals 1, which means k, which is the scalar multiple that we're using to get u down to a unit vector, is 1 over the magnitude of vector u. All right, that was a little bit tricky. So here's what we're going to do. Now we have the velocity of this vector, and we have the direction of the vector, ku. So a unit vector, so this is k, right? So the unit vector in the direction of u is ku. So therefore, the unit vector in the direction of vector u is, and I'll just, I'll fit it here, is k, which is here, 1 over the magnitude of vector u, ku times u. Yes? Now, we have the magnitude and direction of the projection vector v onto u. So let's finish this up. Therefore, the projection of vector v onto vector u is equal to the magnitude of vector v cosine of theta. This gives us our magnitude. Times 1 over the magnitude of u times the vector u. And that is going to give us our direction. Okay, let's put this thing to work. First we're going to look at B, which is going to deal with, so this was when the relationship between, when the angle between the two vectors was less than 90 degrees. This is what we came up with, okay? And now we're going to do one where the angle between them is between 90 and 180. All right, so here we're going to need a diagram. Vector u, vector v, somewhat arbitrary, and an angle in between them of theta. We've got point A, point B, point C. And now, if we're talking about the projection of v onto u, then we're kind of extending this line, and we're coming up from a right angle. And that tells me that this piece right here, let's call it AD again, with a right angle triangle, represents the projection of v onto u, and you can see that it is going the opposite direction of of u. And this is a terrible 180 degree line. Should make sure that's clearly flat. Okay, so this then right here is the projection of v onto u. Now, the magnitude of v onto u, the magnitude of projection v onto u is now equal to the velocity, so I keep saying velocity for v, the magnitude of vector v times the cosine of 180 minus theta. Why do we say that? Well, because we're creating another angle here. Let's call it alpha. And that angle is 180 minus theta. Okay, it's supplementary angle. And we're still talking about cosine because we still have adjacent and hypotenuse. Okay, so what does this reduce to? Well, property of cosine is that, so the magnitude of vector v, the cosine of 180 minus theta is equal to negative the cosine of theta. You have to get your trig sheet out. And then this is just two factors, and it's one of them is negative, so we're going to have a negative sign out front times the cosine of theta. Now you can compare this to what we got in the situation in A, where the angle was between 0 and 90. We had this same statement, but it was positive. So now it's going to be negative, okay? The direction, maybe put it in red. The direction of the projection of v onto u is opposite the direction of u. So we're going to get a negative value of k. We're going to get a negative value of k because we're going to be talking about a unit vector, that a multiple of a unit vector that is going in the opposite direction of angle of vector u. So when we multiply u by k to get ku, it's going to be going the opposite direction, so k must be negative. Let's do that in note form. So from part A, we found out that k is equal to 1 over the magnitude of vector u, but now we're going the opposite direction, so we're going to end up with negative that value. Okay, so a unit vector that goes the same direction as u would be 1 over u times u, just like we did in A, but this time the unit vector going the opposite direction, the unit vector in the opposite direction is, I should say 2u is negative 1 over the magnitude of u times the vector u. Okay, so here's our direction, opposite angle, opposite vector u, and here is our magnitude. The magnitude is negative vector u. Sorry, the magnitude is negative because it's heading the opposite direction. So to wrap that up in red, in this case, when our angle is between 90 and 180, the projection of v onto u is equal to negative the magnitude of vector v times the cosine of theta times negative 1 over the magnitude of u times the vector u. Again, this right here gives us the magnitude. This right here gives us the direction. That is of the projection of v onto u. It's our AD right here. And what happens if you have two factors that are negative and you multiply them by each other, or you have two negative factors in a string of multiplication? Well, it comes out positive. The magnitude of v times the cosine of theta times 1 over the magnitude of vector u times vector u. So here's your final reduced formula for both situations. In summary, you might say, well, why did we do both if it's the same from 0 all the way to 180? Because if you are talking about the magnitude and direction together, the whole vector, the whole projection of v onto u, then you're right, it comes out positive both ways. But if you're just talking about the magnitude, or you're just talking about the direction, then that negative sign is incredibly important because you'll only have one negative factor in the magnitude discussion and one negative factor in the discussion with regard to the direction of this projection. So example 4, this is projection of one vector onto another. We're going to determine in A, there's going to be two parts. We're going to do A and B. We're going to determine the projection of u on v. We have vector u right here. We're told that its magnitude is 5. And we have vector v. We're told that its magnitude is 1. And the angle in between them is 50 degrees. There's actually 4 parts to this one. A, B, C, D. All right, well, since the angle is between, let's say this, since theta is between 0 and 90 degrees, magnitude is given by the projection, so the magnitude of the projection u onto v is equal to the magnitude of u times the cosine of theta. Plug in what we know. Magnitude of u is 5, theta is 50, in the calculator 3.21. So that's the magnitude, and the direction is the same as the direction of vector v. Direction of the projection of u onto v is the same as vector v. B, we have another drawing. We're going to go P on Q. Here's vector P, has a magnitude of 20. Here's vector Q, has a magnitude of 30. Angle in between them, 120 degrees. All right, well, it's greater than 90. So its magnitude then, magnitude of the projection of P onto Q is negative the magnitude of P times the cosine of theta. Plug in what we know. Magnitude of P is 20. Cosine of 120 degrees. And that equals 10. So the magnitude is 10. So if we're just talking about direction, you see how it ended up coming out as a positive number because we're not talking about direction at all. We're talking about the magnitude, and it's going to come out in the direction of, in the opposite direction of vector Q. If we could kind of throw that into a diagram, we end up with this is the vector that we're talking about here. This is the projection of P onto Q. It has a magnitude of 10, and it's in the opposite direction of Q. Direction, opposite vector Q. Clearing. C. C says determine the projection of D, which gives us as 2, -3 on C, defined by 1, 4. All right, so now the projection, not red, the projection of D onto C is equal to D dot C over C dot C times vector C. Let's talk about where that comes from. Without going into a big proof and detail, we can just put as a little side note 2 equivalent statements for the projection of, I'm going to generalize here, I'm going to say V onto U. We've already used this one here. It's the magnitude of V times the cosine of theta times 1 over the magnitude of U times u. Okay, we've used that one. That's what we used in A. Another way to write this is the dot product of v and u over dot product of u times the vector v. So again, a magnitude and a direction, and here a magnitude and a direction. I'm not going to prove that to you right now. We're just going to assume it, and we're going to use it so that you can do it both ways. And from here, I get to sub in what I know. So if I'm taking the dot product of DC and CC, then here in the top, we have the dot product of DC is the dot product of 2, -3, and 1, 4. And the denominator, remember the dot product of a vector and itself is simply the magnitude of that vector squared. But here we're gonna do it step by step here. So we've got 1, 4, dot 1, 4, and then out here we still have the vector c, which is 1, 4. All right. Taking the dot product of these guys, I'm taking the product of the first two numbers, so 2 times 1, so my numerator, 2 times 1 plus -3 times 4. And in the denominator, I've got 1 times 1, which is 1 squared, plus 4 times 4, which is 4 squared. And then out here I still have 1, 4. Reduce the brackets. 2 minus 12 is -10 in the numerator. The denominator is 16 plus 1, which is 17. Times 1, 4 on the outside yet. And so now I just have a scalar times this vector, which is just going to give me -10/17 times 1, which is -10/17, and -10/17 times 4, which is -40/17. Okay, so this is the vector. That is the projection of D onto C. We used a different formula here, an equivalent formula. Worked it out. And this is in the in order to determine whether it's in the same direction as C or the opposite direction of C, we would kind of look at where C is going. So you could think about it this way. C is somewhere over here. Nope, somewhere up here. 1, 4, positive, positive. And our final answer is in negative land, -y and -x. So it's going the opposite direction. Opposite direction to vector C. Again, this is positive, 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 and this one's negative, negative, opposite direction. Part D just says to illustrate the things that we've already done. I think I illustrated A and B, but I'm happy to illustrate C a little bit better. So here is our coordinate plane, x-axis, y-axis. We've got the vector D, which is 2, -3, so let's say 2, -3, coming out about there. Okay, and we've got the vector C, which is 1, 4, 1, 4, coming out about there. Okay, so then and I should label our vectors. Here's C, here's D. I'll label it on the other side. So then the projection of D onto C, there's my extension of vector C. I seem to tail in every time. Looks coming up perpendicular from here. Is this vector right here. in the direction opposite to vector c, and this point right here is the point -10 over 17, -40 over 17. Okay, this little blue arrow, that is the projection of D onto C. Projection of D onto C. Example 5, last one. Example 5, dot product in sales, of course a financial application. Shoe store is selling 350 pairs of amazing shoes, Excaliburs, and they're going to sell 275 pairs of Camelots. The Excaliburs sell for $175 a pair. It's pricey. Not as pricey as the Camelots, $250 a pair. All right, this is what they're selling in a year. We're going to write a Cartesian vector S to represent the number of shoes sold. So a vector representing number of shoes sold. That's in 1 year. We're going to call that vector S. And all we're going to do is take the pairs of Excaliburs sold and the pairs of Camelots sold as our defining coordinates. Plug those in there in a vector. Okay. Now we need a Cartesian vector to represent the price of each pair of shoes, or the price of the types of shoes. So it would be vectors for price of the shoes. All right. The price of the shoes, if we're starting with Excaliburs and then Camelots, are going to be 175 for the price of the Excaliburs and 250 for the price of the Camelots. So now we're starting to see where these two vectors are, how they're going to interact a little bit. We've got a quantity and we have the price of these shoes. So we're going to find the dot product of these things. This is a bit of an exploration. See, dot product of S and P. We shouldn't write it that way. The dot product SP. And then we're going to talk about what it represents. All right, well, the dot product S dot P is equal to, we have these in Cartesian, so we're just going to rewrite them, 350, 275 dot 175, 250. So now we're going to take the first times the first and the second times the second and add them up. Hopefully you're making some mental connections here. We're going to take the quantity sold, the number sold of Excaliburs, and multiply it by the cost of each Excalibur. And then we're going to add the number of Camelots sold times the cost of each pair of Camelots. And we end up with 130,000 as a value. Well, what is that value? Well, if we took the amount of money that they're making off of Excaliburs and the amount of money that they are making off of the Camelots in a year, the total revenue off of these pairs of shoes for the year is $130,000. So what's happening here? The dot product represents the revenue. $130,000 from sale of shoes. So this was a pretty simple application. You might say, well, I'd never count it that way. I could just multiply it. I could just go this times this plus this times that. All it is to show you that you can end up using vectors, and this gets into something called matrices, in order to do more complicated calculations, if there were more factors or if there were a greater variety of shoes, etc., things like that. Anyway, practice problems are on page 384. You are responsible for knowing how to do numbers 1 through, say, 20. Thanks for listening.